In this video, we look at another example from section 13.4, 13.5, okay, related to the acceleration decomposition problem, okay, where t is the unit tangent vector and n is the unit normal vector, and why is this not, there we go. And a sub t and a sub n are called the normal components of acceleration. Okay, so I just wanted to do another example, not a circle, an example where the curve r of t is not a circle. Not a circle was one of the last examples. So let's take a look here. Let's say that our curve r of t is equal to the integral from 0 to t cosine of z squared dz, and the y entry is the integral from 0 to t sine of z squared dz. Okay, believe it or not, this is actually going to be a doable problem, even though the x entry and the y entry of the curve look rather complicated. Okay, the computer can plot this if you wanted to go to Mathematica and do a parametric plot. Do that in Mathematica. What you're going to find is that a plot of this will look like something like this. Okay, this is an example. This is something called the Fresnel spiral. Okay? And even though the curve itself looks rather challenging, let's remind ourselves that what we need to do to find, say, the velocity vector v of t is to take the derivative of the x and y entries, and the way you do that is by using the fundamental theorem of calculus. And the fundamental theorem of calculus says that the derivative, say, with respect to t of the integral from 0 to t some function f of z dz is just that function evaluated at t. Okay, so using the fundamental theorem of calculus here, the derivative of this first entry is just going to be the cosine of t squared and the sine of t squared. So there's your velocity vector. Okay, the magnitude of v will be equal to 1, so that the unit tangent vector, which is v divided by the magnitude of v, will just be cosine of t squared sine of t squared. So there's the unit tangent vector. I'll show pictures of this in a second. We'll just deal with the computations first. Okay. And then you'll need, so let's see here. T prime is just equal to, because the magnitude of v is 1, t is just equal to r prime. Okay. So if you go to your acceleration vector, which is r double prime of t, or in this case just t prime of t, okay, when you go to the second derivative, you'll get from the chain rule 2t, derivative of cosine is negative sine of t squared, derivative of sine is 2t cosine of t squared. So there's the chain rule kicking in for you. Okay. And then, let's see. And then when you take the magnitude of t prime, okay, you'll get, let's see, what will you get? You'll get this times this, this times this. You'll get 2t when you take the magnitude. Okay? 2t is the magnitude of t prime. Okay? And therefore, when you take, to find the vector n of t, which is t prime of t divided by the magnitude of t prime of t, the two t's will cancel and you'll just get minus sine of t squared cosine of t squared. Okay? So here are your vector for t. Here's your vector for n. Okay? And again, you can check, you should check, that t dotted with n is equal to 0, which implies that t is perpendicular to n. In the last video we showed that t is always perpendicular to n, but here you have another example to check. Dot product this vector with this one and you will get 0. Okay? So where do you go from here? Right? Where you go from here, you take a sub t and a sub n. You need to take your acceleration vector, dot it with t, and to find the normal component of acceleration, you take the acceleration vector dotted with the normal vector. Okay? And what you'll find in this problem when you do those dot products is that you'll get 0 for a dotted with t, and a dotted with n, you will get 2t. Okay? So what this says is that your acceleration vector is 0. The acceleration doesn't point any, not point in the t direction. The acceleration doesn't point in the t direction, and it only points in the normal direction. Okay? And what I see here that that a sub n is equal to 2t is that you can see here that your acceleration vector, a of t, gets longer the longer you stay on the curve, the longer you follow the curve for. Because n is a unit vector and its magnitude will just be 2t for the whole acceleration. So as t gets bigger, the number in front of the normal vector gets bigger, and so that means that the vector is getting longer. Okay, so we can see all that played out. Here are your computations. Okay, and we'll bring in this example. Just write these down and compare to what I'll show you in just a second. Okay, here we go. I'll bring in my demo. Okay, here's the curve that we're talking about, and it is that spiral. Okay, this is the way the computer represents the curve that we just did. Here's how I typed it into the computer. X is the integral of cosine of z squared, and z is being integrated from 0 to t. I mean, those are hard functions to work with, but if we're just doing the acceleration decomposition problem, here we can see the blue vector is the acceleration vector. As you follow the curve for more time, as promised, can you see, whoops, the acceleration vector was getting longer and longer and longer. Okay, until the farther you go, ooh, that's kind of hard to see. See, as I move more along the curve, now I'm at this part of the curve, the acceleration vector is quite long. Okay, and you can see here that there's the normal vector. The acceleration, this vector, is always pointing only in the normal vector direction. The blue vector doesn't point any in the red tangent vector direction. Okay, so there's a plot. If you want to check any of your computations, you can check your calculations. Here's your curve. It'll show you your velocity vector. Here's your acceleration vector that you can check. It'll compute the unit tangent for you and the unit normal. And here the square root of t squared is t, so the t divided by t's cancel out if you do a little bit of simplifying yourself. And then you can see here that check the tangential and normal components. If you take the acceleration dotted with the tangent vector, you get 0, a dotted with n, and you get 2t. Okay. Now there is a separate computation here that I want to point out, the concept of curvature. And we could spend a full course on this topic. Okay. This course would be a course called differential geometry. But you could spend a lot of time, so let me define the curvature, add a page below. Okay, so let's see here, curvature. Here's the easy way to compute, well, not the easy way, but the easiest way to write it. The curvature is typically used by the letter kappa, okay, or k. And the curvature is defined to be the normal component of the acceleration divided by the velocity dotted with the velocity. Okay. Otherwise known as v dotted with v is also called the magnitude of the velocity squared. So you can write the curvature as the normal component divided by the velocity squared, the magnitude of the velocity vector squared. But sometimes the magnitude of the velocity, you also call that the speed that you're moving along the curve, since speed is a scalar and the magnitude of a vector is a scalar. You call the magnitude of the velocity vector the speed, and therefore the curvature is the normal component of acceleration divided by the speed squared. Okay. You can then rewrite this formula to be this interesting formula that the normal component of acceleration is the curvature multiplied by the magnitude of the velocity squared. Right, so if you know a curve's curvature and its speed squared, you can get the normal component of acceleration. Or if you know a curve's curvature, or if you know a curve's normal component of acceleration and its speed squared, you can find the curvature. So it's a tricky little formula, this one, and it would take a bit of time to discuss. But what we can see here is that the curvature for the spiral, the normal component of acceleration was 2t, okay, and the speed was equal to 1. So what we're finding here for the spiral, the curvature was 2 times t, which meant that the longer you stay on the curve, the more curved the curve gets. So if you look at this plot here, the more you follow the curve, you're getting into this tighter spiral. The tighter the spiral, the more curved the curve is. If the curvature is 0, that means that you're along a straight line. A straight line has no curvature. Here, the curvature is only a little bit, right? Because the curve is essentially straight there a little bit. Curve's not too bent. And then the longer you stay on this curve, the curve gets tighter and tighter and tighter. Okay, so this is a good example of a curve that's used in highway design. It's kind of like the curve for your off-ramp. Okay, that you're coming off the highway, and once you enter the curve, the curve gets tighter and tighter the longer you stay on it. And since force is equal to mass times acceleration, the normal component of acceleration is telling you how much force you're feeling to the outside, pushing you to the outside of the car. So this curve is one where the forces you feel build gradually as you move along the curve. Okay? So there's a kind of an intermediate example, medium example of the computational difficulty for computing normal and tangent normal components of the acceleration and using what you found, your velocity and normal component, to compute how curved a curve is. Okay? So in the next video we'll look at a specific example from the textbook.